5 minutes warning or no?
Yeah, please, please. Thank you for your introduction. So please turn off the light. So light should be turned off. Okay, thank you very much. So I'm Isao Hayakawa. I'm going to talk on the theory of the classical and quantum Penrose effect and anomalous heat relaxation. This is only the talk which includes the quantum effect in this symposium. And this is based on the collaboration with Amit Kumar Chatterjee and Satoshi Takada and Tanfan Bu. So, so good. Sorry, I forgot to put. Wait. Okay, sorry. Okay, so this is the contents of my talk, and firstly, I will introduce what is Penrose effect, and in the second part, which is main part of this talk, which consists of the two parts. One is based on this paper, and another one is based on this paper about the quantum dot Penrose effect and quantum Penrose effect with exceptional points. And in the final part, not third part, I will talk on some modularization of the Penrose effect based on this paper, and I will conclude my talk. Okay, so what is Penrose effect? So the last Penrose, who was a junior high school student at that time, found some interesting non-equilibrium relaxation process. At that time, he put the ice cream mix in the refrigerator to get to eat. He wanted to eat the ice cream, but he found that initially hot one cooled faster than the initially cool one. And 6 years later, with the idea of the Professor Osborne, he published a scientific paper in 1969. This is a last Penrose, and this is a D.G. Osborne. This is a result of their paper. Instead of using the ice cream mix in their paper, that they used water, pure water. And horizontal axis is the initial temperature, Celsius, and this is the time to start freezing. So you can find there is a peak around here, around 20 or 30 Celsius. So, and time to start freezing decreases with temperature. That is very counterintuitive. But it's very controversial. So actually there is a poor reproducibility. In the recent paper about 9 years ago, Barrage and Linden published a scientific paper to reproduce to try to reproduce the Penrose effect by using the very controlled experiment. So they have also collected experimental data. So there are a lot of the scattered data, so nothing can be concluded from these data. And red one is red data points are the result of the last Penrose and Osborne. So there's the peak around the 20 Celsius. But the latest well-controlled experiment indicates green one. There is no peak. So the time to start freezing is increased with the initial temperature. So in that sense, original Penrose effect has been denied by well-controlled experiment 9 years ago. However, now people believe the existence of Penrose-like phenomena in the different context. Actually, 1 year later of the such experiment, negative experiment, there are 2 theoretical papers published in the PRL and the PNAS. So one is written by the Spanish group by La Santa et al., in which they used granular suspension, and they control the initial non-Gaussian parameter, which is kurtosis. So if we have a positive kurtosis, the cooling rate is faster than the Gaussian situation. So this is Maxwellian. So the black one is a non-kurtosis, zero kurtosis, and this is a negative kurtosis. So there you can find the crossing of the granular temperature at the time. So this is a kind of the new finding of the Pember effect. And interestingly, they also found the inverse Pember effect in the heating process. So negative kurtosis has accelerated of the heating rate. So there is a crossing around here. So this is one interesting finding by the theoretical calculation. Another one is Liu and Ratz. They discussed the double potential. So this is a cartoon from their paper, but they have not analyzed this complicated landscape. They have analyzed a very simple double potential in the theoretical theory. They found actually the slow relaxation. Yes. Oh, this is a theoretical one. So in the next slide, I will show you the counter-experimental result to this cartoon. So anyway, if there is a trapped potential, we can observe the slow relaxation if the particle is trapped in the local minimum. Actually, this is an experimental result by Kumar and Beckhofer, which was published in the Nature in 2020. They have prepared a double potential by using the optical tweezer, and they have also used the colloidal particle by trapped by the optical tweezer. And so the temperature is defined by the distribution function, not the temperature for the environment. So, but they analyzed the distance between the non-equilibrium distribution function and the final destination, which is characterized by the equilibrium distribution function. So, so distance exhibits such interesting time evolution. So cold one does not evolve at all, but warm one has very long time to relax to reach the final destination. But the hot one has a quick decrement of the distance to reach the almost final destination quickly. So this is because this warm one might be trapped by the local minimum in the potential. So this is a experimental evidence to have a Pember-like effect. Then last year, there was a report of the quantum Pember effect in the experiment. So this is a cartoon in perhaps this paper. So they also used a trapped optical tweezer by using the atomic gas instead of the colloid. And this is a kind of the qubit, simplified qubit. And they compare the time evolution of the atomic gas between starting from the equilibrium one and the non-equilibrium one. So to make the non-equilibrium one, they have added external field to get the tilted situation of the spin. So, and they observe the entanglement asymmetry in the time evolution. And then they confirm the existence of the crossing point in the time evolution, the entanglement asymmetry. So interestingly, there are two simultaneous experimental reports to observe the quantum Pember effect. And this is a theoretical paper, I think. So this is advocated by the physics viewpoint, APS physics viewpoint. And the number of the paper of the Pember effect is rapidly increasing like this. So you can find almost number of the paper in archive is negligible until before the 2020. And as Lu and Rat and Rasanta et al. Have posted their paper in archive in the 2016, 1 year before their publication. Then still number of the paper is very negligible. And Kumar Beckhofer posted their paper on archive in the 2020. There is some increment of the number of the Pember papers. I also posted one paper in the 2020. And the red one is a quantum Pember paper. The first paper appeared in the 2019, but it's almost negligible. And I posted the two papers in 2023. This still we found a very small number of the quantum Pember paper. But last year, situation has been changed very drastically like this. So number of the Pember paper reached 50, and the number of the quantum Pember effect paper reached 40. So this is 8 times larger than the previous year. So the very quick, rapid increasing of the interest of the quantum Pember effect. That number of the Pember effect, a number of the paper on the Pember effect is still limited. So you can follow everything, so every paper. So this is a good timing to start study the Pember effect. So now we move to the main part. Okay, so first read, I would like to talk on the quantum Pember effect by using the quantum dot. So quantum dot is coupled to the left and right reservoirs. Reservoirs are characterized by the chemical potential and the temperature. And we assume that the chemical temperature in both reservoirs is common. That the chemical potential can be different. So in that sense, if the chemical potential is different between two reservoirs, there is an electric current between this and another reservoirs. And the Hamiltonian consists of three parts. This is a system Hamiltonian, the reservoir Hamiltonian, the interaction Hamiltonian. But I skipped the detail of the Hamiltonian form. But I analyzed only the one quantum dot. And fortunately or unfortunately, this under the wideband approximation of the Anderson model, this is a quasi-classical, so the off-diagonal element is decoupled to the diagonal element. So that means the one quantum dot has only four states. One is a W occupied, and one is a upspin and a downspin and empty. And so we need only to analyze the 4x4 matrix like this. This is a time evolution, a quantum mass equation but it's almost the same as a classical mass equation. So the evolution matrix is determined by the Fermi distribution function in both reservoirs. So this is a repulsion, so penalty of the W occupied state. U is a W occupied state, and this is the chemical potential. So this is a well-known chemical Fermi distribution function, and we have introduced some notation, and this is the evolution matrix. So it's easy to solve this problem because this is a kind of the exercise for the junior student or sophomore student. So the protocol to observe is that we initially prepare the equilibrium setup or non-equilibrium setup, which has a different chemical potential in the different chemical potential, which generates the electric current between this and this. And this is an equilibrium setup, so chemical potential is common. And so we quenched into the same state. We quenched these two systems into the same state, which has a common chemical potential and the common temperature. And we follow the time evolution of the density matrix based on this equation. And so if we can follow the time evolution of the density matrix, and the density matrix element cross, we regard this system as exhibit quantum Pemberton. And if they don't cross, no Pemberton. And this is the final destination. So this is a definition of the local temperature based on the von Neumann entropy of the quantum dot. This is the local energy of the system. So during the time evolution, you can find the crossing here. And there is another crossing around long time region, but it's not so important. But anyway, we have definitely observed the crossing. It's a kind of the Pemberton. And even when we are interested in the local energy, there is a crossing here, and von Neumann entropy exhibit crossing here, and the KL divergence, which is a relative entropy, and one of the monotonic measure. So this ensures that monotonic decreasing with time. So this KL divergence also has a crossing here, around here, and around here. And so there are 2 times crossing. So far, we have demonstrated the existence of the Pemberton-like effect in the Anderson model. But it's fortunately or unfortunately, the system is quasi-classical. So because of diagonal element does not play any role. So we needed to know the pure quantum effect. So, and the model of the open quantum system in the open quantum system may have an exceptional point during the time evolution. So minimum model to satisfy above requirement. Yes, yes.
This is such a simple model.
Right.
Do you have an understanding of why it's happening? Does it depend on the quench rate or
Yeah.
do you have an understanding of what's going on?
Yeah, almost. So no, of course, I skipped the detail, but I have drawn the phase diagram, how to depending on the quench rate. So no, quench rate is infinitely large, but depending on the initial condition, when we can observe the Pembra effect and when we cannot observe the Pembra effect.
Is there an understanding?
Well, understanding is basically, intrinsically, we can often observe the Pembra-like effect if we control the initial condition. It's not so difficult because, initially symmetry is different, so the cooling rate is different. That is a current common understanding to observe the origin of the quantum Pembra effect. So anyway, this is a model, a pure quantum model. It's still very simple model. So the two-level system, which has a gap delta, and the electric field with the frequency omega is emitted from the outside, and this is coupled with the environment by the dissipation rate gamma. And this has an entanglement effect because this ground state, these two elements are the diagonal element, and this is a non-diagonal off-diagonal element, and so diagonal element coupled to the off-diagonal element. Fortunately, this EG and G is different, so that this is not characterized by the symmetric matrix, and because gamma evolution is a little bit different from that with each other. And delta is a parameter which is proportional to this delta, and D is a dielectric electric field which is coupled to the omega. So this simple model characterized has a such characteristic eigenvalue depending on the dissipation rate and the electric field. So the previous analysis corresponds to this region, so which has only the imaginary eigenvalue. So there is an imaginary element here in front of the density matrix, so the previous pure real eigenvalue corresponds to the pure imaginary eigenvalue. So this is a previous region which I analyzed, and now that we have a lot of the variety of the eigenvalue distribution, not the distribution, eigenvalues. So A1 and A2 has a complex eigenvalue, which has an oscillation in the relaxation process. So this region and this region. And C and D is a second order. On the line of the C and the D, there are second order exceptional point, which has a degenerate of the eigenvalue. And this is a critical point, which is a third order exceptional point, which non-zero eigenvalue, all non-zero eigenvalue are degenerated at that point. So still, the model is very simple, so that we can analyze this model exactly by using this protocol. So that we prepare one initial condition and another initial condition, coincident to the, for example, on the line of the C or D exceptional point, by using the master quantum master equation, which is this one. So density matrix has a 3 degrees of freedom because one is a conservation of the probability, and so then we can solve the problem. So for example, the solution on the line C or D, we have such kind of the solution. So interestingly, in addition to the exponential damping mode, we have algebraic decaying mode because of the existence of the exception point. So this is the right eigenvector, and this is the left eigenvector. So the difference between the two systems in the ground state, GG element, diagonal element, which has this algebraic term. So it is quite easy to find 0 of the delta rho GG in this equation. So that means if we have an exceptional point, it's quite easy to find the Pemba-like effect. Actually, you can find the crossing here and the second crossing here in the evolution, time evolution difference of the density matrix element. And this is the von Neumann entropy on the first crossing and the second crossing. And this is the energy difference between the two systems. And this is the first intersection and second crossing. And this is the temperature difference based on the these two quantities which exhibit intersection here. So now the quantum Pemba effect. We have confirmed the existence of the crossing in a simple two-level system. And if we are interested in the complex eigenvalue region A1, this exhibits oscillation. So because of the existence of oscillation, so we have a lot of the intersection, multiple intersections. So this is a red one is evolution of the initial condition 1, and this is blue dotted one line exhibit time evolution of the initial condition 2. There is a crossing here, 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 here. And the energy also exhibits multiple crossing, and the von Neumann entropy also has a multiple crossing. Then temperature, defined by the von Neumann entropy and the local energy, exhibit very complicated oscillation. And in some situations, we can observe the negative temperature. And there are multiple, infinite number of the crossings. So we can say that it's quite generic to observe the initial Pemba effect if we have such kind of the time evolution. Now that we still have a time to argue the more general aspect of the Pemba effect. So instead of using the quantum system, I focus on the classical master equation in this region, in this part. So some majorization of the majorization Pemba effect. So far, I presented some example without any unified view. So as briefly indicated, we don't have a unified understanding because I presented some example, and another person presented another example. But we want to know what is a unified view. And so that I used local temperature based on the local von Neumann entropy and the local energy. But this is controversial. We have a lot of the possibility of the other choices. And as I said, so the Kerr divergence is different from the other quantities. So the Kerr divergence has a monotone measure, so because it simply decreases with time. If the equation satisfies the CPT property. CPTP is completely positive and completely trace preserving property. So And so the monotone measure is important to characterize such evolution. This is a more strict attitude. And also, we have, in the second part, I have prepared a different initial condition. And as I indicated, if the one is in equilibrium and another one is non-equilibrium, the symmetry is different, so that it's not surprising to observe the crossing in the time evolution. But if we start from the both system starts from the equilibrium situation, the Gibbs state. So this is a more strict approach, or more, more strict approach. And that people, so far people discussed, for example, only the Kerr divergence or the L1 measure or L1 distance or something like that. So only the one monotone measure, even when we observe we are interested in the monotone measures. But we don't know the behavior of the other monotone measures. For example, if we observe the Pember-like effect when we use the Kerr divergence, we may not observe the crossing in the other monotone measures. So I'd like to focus on such aspect based on this paper with Tan Fa Bu. 5 minutes, okay. Okay, this we have discussed. Okay, that's enough. So what we have done is, for example, this is a specific measure of the crossing, but we want to discuss the condition that all measures exhibit the crossing like this. So the basic equation is a classical master equation. This is the evolution matrix. Evolution matrix elements satisfy the detailed balance condition. And so we want to get the condition of the Pember effect. This is starting from the hot initial equilibrium condition and the warm distribution equilibrium condition. Distance is larger. And finally, distance is opposite. This is a condition of the Pember effect. So maybe I should skip the detail, but this is the P tilde, Q tilde is a permutation of the probability distribution of the PQ to satisfy these inequality. And Lorentz curve, we have introduced a Lorentz curve to connect the zero and this quantity. And some modularization is defined by if the Lorentz curve P pi lies above the P prime pi, always like this. So that I don't think that you can follow this definition. So that I can put that here like this. So some modularization, this inequality satisfies these three conditions. So this is the red one, the P prime pi, and this is the blue one, the P pi. So this is not independent. So there is a stochastic matrix to convert it in P to the P prime. So these are connected. And we have introduced such quantity, and there is a function, convex function fx, to satisfy these conditions. And L1 measure satisfies this quantity for any g, which is a real number. So this is a sum modularization. It's a little bit abstract concept. So definition, sum modulation Pember effect is of the definition is something like that. So this is a so initially probability is less than this one. So this is the final goal of the equilibrium situation. And the definition is something like that. And we are going to present the whole result. Result one is the sum modulation painful effect is equivalent to the painful effect to all monotone measures. And the result to the sum modulation painful effect in the long time occurred if and only if this condition is satisfied. And the probability distribution function near the final stationary state is expanded around the final goal, equilibrium Gibbs measure. This is the slowest relaxation mode. This is the eigenvalue of the smallest eigenvalue near the zero. And this is a light eigenvector. And the result three is that the condition, this is in the introduction, I skipped the introduction of this concept, but this is introduced by the Liu and Lutz a long time ago. This coefficient of the slowest eigenmode characterizes the Pember effect. That is true if we start from the local equilibrium state in the initial condition. So in this situation, but this is what we found. This is only the necessary condition, not the sufficient condition. And the result four is the whole arbitrary t over t is less than the tw and the th, and the energy level epsilon n. There always exists a transition matrix to show the time modulation Pember effect. Perhaps I am afraid that you cannot follow such statement, and because time is limited, I skipped the proof. Read paper if you are interested. But we demonstrate that this graph by using the F divergence. So F divergence is one of the monotone measures, and we can control the alpha so that we can introduce the continuous number, infinite number of the monotone measure by using that. It has, which is a crossing point depending on the alpha, does not exhibit any convergence, so that it's increased with alpha.